So here, here's another example. Okay, here's an example for L equals to 7. L equals to 7. Okay, that's an example. So let's count. 1, 2, 3, the corner frequency. 4, also the corner frequency. 5, negative, positive, negative, positive, negative. There are a total of 9 alternating points where the error changed sign from one point to the next. Okay. So this is again an optimal filter design. And also note that we do have different tolerance. So here in the pass band, the maximum error is delta 1. Whereas in the stop band, the maximum error is delta 2. Delta 1 and delta 2 does not have to be equal. And that depends on the definition of how you define your weighting function, how you want to penalize the error. If you put a large weight somewhere, that means that we want to minimize the error by minimizing the error more than another place. So this one really is very flexible. Okay? You can define if you care for the error more in the pass band or in the stop band. It's up to you. Okay? Now the next example here, that's an example of exactly what I'm talking about. So note that here the result optimal design, in this case it's a low pass filter. You see the pass band error is smaller than the stop band error because of the simple fact that we put a higher penalty for the pass band than the penalty for the stop band. So this ratio 1 over k. Okay? That gives you a flexibility to whether you want to focus on the stop band more or focus on the pass band more by giving it a different weight to different regions. Okay? And in the end, we see that the weighted error function is kind of equal. The maximum weighted error function is equal for the stop band as well as the pass band. So that after weighting, the error is equal ripple. So this is an equal ripple property. Any such an optimal filter has equally high ripples in the stop band and in the pass band and stop band after weighting. The ripple is going to be equal. Okay, so that's kind of nice. That's kind of nice. You can see in terms of minimizing the maximum error, of course, the result is the best result you can get is going to produce equal ripple frequency responses. Equal ripple, did you do? No. Equal versus equal ripple. That means this is a ripple. This is a ripple, that's a ripple, that's a ripple. So the height of the ripple is the same throughout. It's the same at all the alternating points. Okay, the ripple, that's the maximum error. That's a ripple. That's the height of the ripple. So next, more examples. Okay? And here, again, we are talking about 7th order polynomial. And the first example on top, part A, has how many? It has 10 alternations. 10 alternations. And you can probably count it. And they mentioned that the theorem itself says any problem? It has 10, right? 10 alternating frequencies. 10 alternation points. Right? 3, 4, 5, 6, 7, 8, 9, 10. Yeah, okay. And it's kind of cool to mention that even though the theorem says at least L plus 2 alternations, sometimes L plus 3. Okay? That's an extra ripple. Sometimes we call the example the L plus 3 extra ripple cases. It turns out that it's impossible to have L plus 4. It's impossible for, at least for low-pass high-pass design, the result cannot have L plus 4. It is impossible. Impossible to have L plus 4 alternations. Okay? And there's a very fundamental reason for that. So it's going to be either L plus 2 or L plus 3. And in the later 3 cases, we have in this case, we have L2 plus 2 alterations, L plus 2 alternations, and L plus 2 alternations. But for part B, we have an extremum at the Nyquist frequency, and for this example, we have an extremum at the DC. Not Nyquist, not at the Nyquist, that's fine. And here, in this example, interestingly, indeed, we still have L plus 2, that is 9 alternations, but we have both extremum at DC as well as Nyquist. Okay, so there are 3 different situations, 3 different kinds of results. That leads to a question. That leads to a kind of hard to answer question. When do we have extremum at Nyquist? When do we have extremum at DC? And when do we have extremum at both frequencies? That's a hard question to answer. That's a hard question to answer. Okay? I say hard because it's kind of by luck. So let me say, let me suggest it. When will we have a extremum at DC? And when do we have an extremum at Nyquist? And when do we have extremum at both? There is no, it depends. Okay, it's kind of random. Right? It's kind of random. Turns out that it depends only on where you set your cutoff frequency. Okay, it depends solely on omega p and omega. Actually, omega p, omega s, the 2 corner frequencies as well as the wave function. I think it also depends on the wave function. But I'm sure not exactly. So anyway, so that's really kind of by chance. Sometimes you do have extremum at DC or DC and or Nyquist. Okay, and exactly what situation do we have extremum at DC and or non-Nyquist? It depends. It's kind of random. It's kind of random. Okay. Any comment? Or it's not that important. Okay. Usually we care about the height of the ripple, not the exact location of the ripple. Okay. And here is what I just said. It turns out that when we design a low-pass filter, we want to find an optimal solution. The alternating points must include the edge. Okay. Whenever we have, if the edge frequency are not alternating frequencies, then immediately we know that there's still room for improvement. Maybe you can further kind of squeeze this extremum up and pull these two down a little bit so that it exactly passes through the corner frequency. There's still room for improvement. That's what I want to point out. This means room for improvement. Room for improvement. 有改善的空间。Any comment on this slide? The pass band edge frequency, omega p must be an alternation frequency. That's the way the textbook says it. And I also mentioned equal ripple, okay? Illustration, this is an illustration that the frequency response must be equal ripple in the approximation band, okay? And again, this also means room for improvement. Room for improvement right here, okay? Because you can imagine we probably can further minimize the maximum error by pushing this down upward and pulling these two extremes downward a little bit so that the overall maximum error can be further reduced. So this is not optimal yet. The ripple is not yet equally high. Okay? The ripples are not yet equally high. That means that we have room for improvement right here. Okay? Okay, so next, let's go through this how exactly to find the maximum, the optimal polynomial. How exactly to find it, the optimal frequency response. So the idea starts with, there's a flow chart in the next slide. So Let me just verbally explain for now. So the idea starts with trying to randomly guess where the alternation frequencies are. Any machine learning, you need to initialize your guess. Okay. So let's say now suppose we just by a kind of clever idea, given the corner frequencies, and we want to design maybe I forgot how many, 1, 2, 3, 4, 5, 6. Okay. So suppose that we are going to design a 6th-order polynomial, if we run correctly. So now we know that is it 6 or is it 5? 3, 4, 5, 6, 7. Let me say this plot looks kind of weird. Okay, let's forget about what exactly else. So suppose that we are designing an L-order polynomial, right? So actually it should be anyway, it could be 5 or 6. Okay, let's say 5 or 6. 6th order or 6th order polynomial. Okay? So we need to randomly guess. Suppose this is 6. Okay? So we need to randomly guess 8 alternation frequencies because we want the final result. If you are lucky enough, the algorithm should converge to a solution which has at least L plus 2 extremes. Okay? So let's just randomly guess, okay, omega 1, this whatever frequency will be the alternation frequency. And we guess omega 2, 3, and omega 4, we guess that the fourth one reaches the corner frequency for path n. Okay? And we guess, now we know omega domain, not the x domain, the low pass design, and we guess that the 5th one is the beginning frequency of stop n, and so on and so forth, and 6 and 7. Okay? So maybe this is a design for 5th order polynomial, I'm not sure. The plot looks strange here. So anyway, so based on the guess of alternation frequencies, you can find a polynomial that actually, so 5th order polynomial, we have 7 equations, but we define 7. So let me just write it down. Okay. Suppose that we guess omega 1, omega 2, all the way to omega 7. Omega 7. And we know that each omega corresponds to an x, right? After the change of value, x equals to cosine omega. So we have these 7 different x. And we are guessing that they are the alternation points. These are the alternation frequencies after the change of value. These are alternation x's, okay? X's. And so now we have quite a few parameters to determine, okay? We want a p of x equals to k from 0 to 5 ak xk. No, x to the k power. So suppose that we need to determine, we want to find the polynomial, right? To find the polynomial, we have 6, so now we have 6 parameters to determine, right? The 5th order polynomial, we have 6 parameters to determine. But now we have 7 equations. We are guessing 7 different x's to be the extreme, the alternating frequencies. So we have one more equation than variables. We have one more equation than variables, right? So turns out that there's a 7th parameter we also need to decide. That is exactly the height of the viewpoint. Delta is also a variable. So let's say this we require, if we define the polynomial as such, and we require we require P of x1 to be delta, and, oh no, not P of x1, I say E of x1, okay? E of x1 to be delta, and E of x2 to be minus delta, and so on and so forth. And E of x7 should be plus delta again. So now we have 7 equations and 7 variables. Is that clear? 7 equations being these 7 equations. And 7 variables means variables are A1, so A0, A1 to A5, and delta. That's a variable, the column vector that we need to determine. And it turns out that if you just write down the equation, we have a 7 by 7 matrix, a system of 7 equations with 7 variables, and we can solve it by the linear algebra. Okay? Is that clear? So you can solve all the parameters, these coefficients for the polynomials, as well as the highest ripple by linear algebraic approaches. By solving a system of 7 equations, 7 variables. Right? Okay so far? Okay so far? So it turns out that this is an equation of 7 times 7, and A0, A5 delta equals to equals to something, okay? So that's how, at least in principle, for the first round. For the first round, we begin by guessing the alternation frequencies, which all have corresponding alternation locations in the x domain. And then we can write down the system equations and solve this polynomial as well as the height of the ripple. But wait a moment. So this is to say, the polynomial we find, okay, the polynomial we find indeed would satisfy all these equations, okay, that's for sure. But what is not guaranteed is that after we find the polynomial, it turns out these frequencies might not actually be the extremium frequencies of that polynomial. Let me say that again. Okay, we solve we find the polynomial. But it turns out that if we just look at the extremium, location of extremium of the resulting polynomial, that in general will not match with the list of the point that you guessed. So after finding a polynomial of some sort, okay, and you can try to find its extremiums. Extrema, okay, plural. You can try to find its extrema, and it turns out that the list of the extrema might be x1 prime, x2 prime, and x3 prime. And in general, they will not just automatically be equal to x1 to the list of the points that we have guessed. So in general, this set will not exactly equal to that other set that we began with. So they're not going to perfectly match. Okay? So then the idea is very simple. Okay? After you just now we just treat these actual extrema as our new guess of the alternation frequencies, and then repeat the whole process. Like there, so this is by iteration. 用迭代的方式，iteration. So by iteration, we just treat these actual extrema as our new guess for the alternation point, and repeat the whole process until the extrema, the distance between the list of extrema and the points of guessing, the alternation point, or guess alternation point, until until the entire process kind of converges. Let me summarize what I was trying to describe. Okay? So at first, you'll need to make a guess. You need to make a guess. Initial guess of as many as L plus 2 extremal frequencies. And then we can calculate the optimal delta. And it turns out that calculate delta and at the same time find that polynomial. That's what is meant by interpolation. Okay? But then after that, we can actually now, in this step, we actually try to find the local maximum. And try to retain L plus 2 of them. Okay? There might be an extra maximum or not. And then we check if the extremal points has changed from last time. Okay? So if it changed, that means the algorithm hasn't converged yet. So then we repeat everything. We get back to replace the list of extremal frequencies by the updated result. And we repeat everything, calculate the new delta. And hopefully delta will just, by iteration, this delta will keep decreasing and until both delta and the list of extremal points converge. So we check the convergence criteria, and finally, if these things don't change too much, we say, okay, we probably have found a close enough approximation to the optimal solution. Because now this is the spirit behind this algorithm really is the alternation theorem. Because we know that the optimal solution has to have this property, where we have alternating a list of x locations where this error function reaches maximum and the change sum. Okay? So this is kind of a clever idea of using this property for optimization without the need of gradient descent in this one. It's by replacement. Hopefully, if the algorithm converges, then it gives us that guarantees the reach to the optimal solution.